What is reaction at point A?
2p.
Yes, of course, 2p. And besides 2p, do we have anything else?
Moment.
We of course have the moment. Now, what's the direction of the moment? Is it clockwise or counterclockwise?
Counterclockwise.
It should be counterclockwise, right? How do we figure that? Because the column is tilted or is being bent toward the right. So the internal moment must be what? The reaction must be in the opposite direction of motion. And that's why the moment must go like this. Goes like this. And this is the internal moment at A, which is MA. Now, let's consider, or let's define that the maximum deflection at point B is, let's call it delta B. And the maximum deflection at point C is delta C. So this profile, we can use another more clean configuration to define it. That means this is our Y, this is our X, and the profile looks like this. At point A, at point B, and at point C. At point B, we call this deflection, this part, delta B. That is the deflection on the y-axis. And the deflection at point C, which is from here to here, we call this delta C. Of course, there's no deflection at point A because it's a fixed-ended support. Now, with this, we actually would know, if you know the distance at the location where these two forces are applied, of course, we also know what is the value for the reaction at A, right? The reaction at A, in this case, we will know that it actually has equals to P times delta B plus P times delta C. So we know that from here, the end moment MA equals to the summation of P times delta B and P times delta C. And of course, you can just write it as P times delta B plus delta C, just like that. Now, what we need to do is to really cut it. And when we cut it, then the free body diagram will look like this. Column like this, and the end moment right here, and also the reaction. Let's use this. This one's MA, and it's equal to P. Right. What happens to actions? To actions, this end we have 2P. And we also have internal, right? Internal moment. So in here, what's the direction of internal moment? The direction of internal moment should go this way. This is the direction of internal moment. Correct? Right? It's in this direction. So the question is, what is the expression of this internal moment? Should it be positive or negative? So let's take what we discussed before and apply it to this example. Now, first, we recognize, I really use both. you recognize that this is our y1 and this is our x1, right? So in this case, let's try to figure out that what will be the positive curvatures in this configuration. Y1, x1. What is positive slope? Positive slope, of course, you know, is like this, right? This is positive. And what will be the positive curvature? Remember, looking at the positive direction for y1. And so you look at this one. The positive curvature means the curve should go starting with a positive direction, and it should be increasing with an increasing slope. That means you should go like this. This is positive curvature. That means y double prime is greater than 0. For this one, it's y prime greater than 0.
Does it curve up, Professor, like you showed earlier?
No.
Or is this case different?
No. That's why I have to make this clarification. Look at this one. Notice what? Notice now we flipped x and y.
That's right. That's okay. Yep.
Right. In this case is a beam, and here we are looking at a column. So the best way is what? And just use the following approach to determine what's the positive curvature. Step 1. Define your positive directions, x and y. So step 1. Define this. Step 2. Define your positive slope, which of course you know how to do it, right? So what is this positive slope? Because once you define the positive directions of x and y, you already automatically establish 4 quadrants, right? You just have to look at the first quadrant and then draw whatever angle in that direction. That's going to give you a positive slope curve, or I'm sorry, positive slope line. So step 2 is draw this. You have no problem doing it, correct? So what's step 3? Step 3 is draw the line along the positive slope and with an increasing slope toward what? Toward the direction of positive y. You see, this is the one how we determine this. It's increasing slope, remember? So when I curved it toward the positive y. That's how we determine the positive curvature. So this is step 3. If you do this, you will never be confused. Is that clear?
Yes. Thank you.
Okay. Now, with this, please tell me what is the slope in this configuration in the free body diagram that we have here? Is it positive or negative?
Positive.
It's positive, right? It's positive. Because the slope, the curvature is positive, and that's why the internal moment, in this case, internal moment, the curvature is already positive. There's no need to change the sign. Just equal to EI times y double prime. Now, while you still remember this concept, let's go to the next page. I will use a blank page to quickly show you the opposite. You remember that from, I don't know which example that we studied this problem, right? We studied this column like this. Actually, it was simply supported. And so it looks like this. You must remember this example, correct? This one is EI, and after summation, we have something like this, remember? Correct? This is simply supported beam button, correct? And we did this one before. And in that example, this is how we define our x and y's. We define our x this way. This is our x, and this is our y. So in this case, look at the positive definition. Now tell me, in this kinematically admissible deformation profile, what is the curvature of this blue curve? Is it positive or negative?
Negative.
Very good. And that's why in this case, we said because what? Because y double prime is less than 0. And what's the moment? The internal moment is positive. And m internal moment is greater than 0. So the only way to work these two together is to say that m internal equals to negative ei of y double prime. But mathematically, you know very well this is actually ei times what? Times negative y double prime. That was y. So that's why it's important to pay attention to the signs of the curvature. When the curvature is positive, then you don't have to put a negative sign. But when the curvature becomes negative, you need a negative sign in order to balance the mass, to make it equal. Because the left-hand side is a positive, so the right-hand side must be positive. That's why we always add this one. Not always. That's why we add this one in some of the cases before. So this is the complete version that we use from the beginning. Now you know why. All right, so we can leave this part just to be here, this comparison. And come back to here. Okay, and now let's take the moment equilibrium. So we need to take the moment equilibrium. That means summation of the moment at point A must be 0. And whichever direction you like to take, suppose we take clockwise to be positive, it's always good to write this down, just to remind yourself. And of course, you can also define otherwise, as long as you are consistent with your definition. That's key. Doesn't have to be positive in clockwise direction, not necessarily, absolutely not. The other way will still work out perfectly. So here, what do we have? Take the moment equilibrium from this rebalanced diagram, and you know we have in m internal, right? Plus 2p times what? Times the variable. And the variable, which is the distance from this point to whatever the point we consider, and that's y1. And this minus ma must be 0, correct? Right? And because m internal is in this case ei times y1 double prime. So we have this ei times y double prime plus 2p times y1 equals ma. And of course, we always like to move. We always have to remove the effect of ei on y double prime. That's why I always write it this way. Y double prime plus 2p over ei times y1 equals ma over ei.